Now it's my pleasure to introduce our speaker for this evening, who is Dr Igor Marković, who's going to be talking to us about the hidden life of electrons. Shall we welcome him with a round of applause?
Thank you, Dan, and for the invitation and for the opportunity, and thank you everyone for coming in such large numbers today to hear me talk about teeny tiny little electrons and what we can see of them. The animation that you see in the background on the title slide is actually my research data. Not important, but keen-eyed amongst you might spot the data later on in the slides. That being said, let me first just introduce a little bit the topic. I know that these lectures are often astrophysics, particle physics, and everyone gets very excited about that. I'm talking about none of that. If you're here for that, you're actually going to be very pleasantly surprised. This is much better. So what I will talk about is a field of physics called condensed matter, or used to be called solid state, but that is actually the part of condensed matter that I'll be talking about. And it is about the electronic behavior in different solid state materials. Why it's important, how electrons behave. I'll give you a very cartoonish pictorial introduction to the behavior of electrons, and then give you a little bit of a flavor of what kind of research I specifically do, because this is the topic that I specialize in. Right. So, to start with, oftentimes, the days that we live in, well, maybe not often, but some people call it the Silicon Age, in the good old tradition of coming up from the Stone Age, from the Iron Age, and so on. The evolution of humanity has come to a Silicon Age, which means that our daily lives are very much preoccupied and dictated by computers and by electronics that we use all the time. The computer I'm showing you this presentation on, the phones that all of you have in your pockets, and so on. And so the question is, how does this go further? Where are we now? How did we get to this Silicon Age to begin with? And there is something known as Moore's Law that some of you may have heard of, which originally started with looking at how computational power increases from year to year. And so here we have some examples of where computation came from punch cards, which some of you might recognize, to relays, to vacuum tubes, and then to the discovery of the transistor, which is when electronics, or rather computation, became electronics and came into the realm of solid-state physics. And from there, we came to integrated circuit boards. And Moore's Law actually says that this computational power is exponential, and that it exponentially grows from year to year. Or rather, the original statement was that the number of transistors that you can put on a chip exponentially grows from year to year, which means that we need to keep making things smaller and smaller and smaller, and at some point we're going to run out of space. We are going to get too small. And so you can even see that here it says single-threaded performance is starting to level off. And so if we want this continued growth in computational power, we need to come up with a new technology, with doing something different in the good old tradition that I showed before, coming from cardboard punch cards to integrated circuit boards through very different kinds of technology. And so there are some ideas that you may or may not have heard of that are already in the works. On the bottom, some of you may have heard of quantum computers. On the top, spintronics, things like racetrack memories, if those are kind of flashy words that occasionally get thrown around. But the idea is that these are technologies based on new principles that we are just discovering, and we are trying to get our computation faster, more efficient, and better for, hopefully, for everyone in the world. And so the question is, okay, but how did we get this big revolution with electronics, and how do we go forward? How do we discover these new technologies? And the original transistor revolution came from our understanding or increased understanding in quantum mechanics and in applying quantum mechanics to solid state materials, specifically for the electronics that we all know and love, on semiconductors and on metals. And understanding exactly how the electrons behave in those materials allowed us to make very tiny, very complicated devices on which we can do all kinds of wonderful things. And so now we want to explore more complex phenomena, different phenomena, and see if we can find something that will then spearhead a new direction in the evolution of computation, and again, make it better, more efficient. But then to try and introduce you to what this understanding was originally of how electrons behave in different materials, I will try and guide you through a little bit of a story and put together from atoms to through molecules to solid state materials, and show you how things behave. And this is just a beautiful illustration of an atomic orbital that illustrates that even if some of this is very abstract and very complex, it can also be very beautiful. So let's start with atoms. What do electrons do in atoms? Well, they through quantum mechanics, we know that they will have certain states, certain ways of behaving that they particularly like. And these are here three that I picked more or less at random that illustrates some of these states, some of these little houses, boxes into which electrons can go and exist in an atom. And one recurring theme in my story of the behavior of electrons will be that when it's all the same color, and when electrons can be in these orbitals which are all the same color, they are happy. And when they're happy, that means that these orbitals have low energy, and that is where all the electrons try to get. The more color changes, the less happy electrons are. They don't like to, change purple to yellow shirt all the time. It's annoying, so they are less happy here. That has a higher energy, and so on and so forth with more complicated orbitals. And so when we have an atom, we have many of these different orbitals in an atom, and then whichever atom we have will have a different number of electrons that we slowly start putting into these boxes. And by the nature of the electrons, they don't like to share space, so you can only squeeze 2 electrons into any of these boxes, and only if their little magnetic moments are pointed opposite. And so they're very exclusive in that sense, no sharing of space. And that means that we start filling things up from the low energy ones, and then slowly go up the energy ladder into the high energy states. And that is going to be, again, a recurring theme on every kind of level of complexity of the material that I will talk about. So if this is the behavior of electrons in atoms, where do we go from there? Well, we can take two atoms that are far apart, and in those atoms, the electrons are in these atomic orbitals. And if we start bringing the atoms closer and closer together, at some point, these orbitals will be close enough that they start to overlap. And when they start overlapping, then the electrons can start hopping from one to the other. Whenever we have that situation where we have a significant overlap, when the electrons can hop from one orbital to the other, they, what we call, hybridize. And what we get is some kind of a compound orbital. So in this case, these would be molecular orbitals. And we'll get two here for the two orbitals that we brought together. And one of them will be where both of the original ones are the same color. As I said, same color, electrons are happy. This is a lower energy state than we had in atoms themselves. But the other combination gives us an orbital that has different colors. And now here, the electrons are not happy. They have to change color if they hop around, and so this is a bad orbital, and that has a higher energy than the original atomic orbitals. But again, this will be a common theme throughout my story and what I will tell you about. And same as in the atoms, we can slowly fill these molecular orbitals with however many electrons we have in the system, starting from the lower energy orbitals and going up. And typically, we won't be able to fill everything up, so we'll have more lower energy electrons than high energy ones. And so molecules, as we all know, are somewhat stable things. And there's many of them around. But okay, where do we go from there? So this is kind of a basic idea of how what happens when we bring atomic orbitals together. And this is all an introduction for what I want to talk about, what happens in the solid state. And so by the solid state, I will generally mean crystalline materials, which means that we have many atoms which have come together in some kind of an organized arrangement like so. So they form what we call a lattice. So the question is then, if we know what happens when we bring two atoms together into a molecule, can we somehow extrapolate that form of thinking into this enormous aggregate of atoms? And the answer is twofold. On one hand, yes. On the other hand, no. So yes will be in these kind of basic ideas that I illustrated, and kind of the first part of the talk and the lecture will mostly focus on what are these common things and how we can see the commonalities between the solid state and the molecules and the atoms. There will be a lot of parallels. But then later on, I will show you why no, and that is because when you put this many, and this is 10 to the power 23 many atoms together, that level of complexity will simply lead to what is often known as emergent behavior, to all kinds of new phenomena that are definitely not easy to predict and anticipate from just simple combinations of the behavior of the constituent materials. And there are no particle physicists in the room. This is why I originally said that this is more interesting, rather than delving down into what are the constituents and how they behave. We, in condensed matter, deal with a huge aggregate of these constituents which bring about completely unpredictable new phenomena. Okay, so how do electrons behave in such complex crystals? Well, let's bring it down from high level of complexity into a little one-dimensional chain of atoms. Okay? I only have 4 here, but assume this is an infinite chain. And I can bring these atomic orbitals together so that they are all the same color. The electrons then like to jump around, no change of color. We are very happy. This is a low energy state. But you can see that we can then bring opposite colored orbitals together in different ways. And the highest energy state would be one where the electron has to change color for every jump it makes. Wherever it goes, it's a different color. It's extremely frustrating, I know, but this is also an option. And because it's really frustrating, it will be the highest energy state. But you can also see that there will be many combinations in between where you don't change color every time you hop, but also you change color sometimes. And generally, there's about as many combinations of how you can put these together as you have atoms in this chain. And so if it's an infinite atom, then we have many combinations. I'll show you one that's kind of in the middle. So instead of changing color every hop, you change color every 2 hops. And as I said, we can then think about the energy of such an arrangement. I said this state where all the electrons are the same color is going to be low energy, and this state where they change color all the time will be high energy, and there's infinitely many, if we have infinitely many atoms, states in between, and so the energy of these states kind of continuously goes from one to the other. And this description, or this way of drawing these states, is what we call electronic bands. Okay, so if you maybe have heard of the term before, this is what we mean, and we depict it in this energy versus something that I wrote K, but which essentially just means how many times do you need to change color when you hop around a space. So it's a diagram in this energy versus K. I will try to keep most of the talk quite pictorial, but I heard that occasionally people want to get their money's worth of coming to a physics lecture, so I have 2 slides with some equations on them. Very, very simple though. So just for those who want a little bit extra, I can tell you that what that K means. It is what we know as a wave vector. It's essentially a spatial frequency, if you will. So a K of this maximal or highest energy state just says that you change color every time you hop, and if I call this distance between 2 atoms A, this pi over the distance across which we change color is the wave number. If that distance is infinite, because we never change color, then we end up with K equals 0. And so all of these bands that I will tell you about will be somehow constrained for the value of K, because I can only change with some highest frequency if I change color from one atom to the next. Okay, this is kind of what the thing looks like if we only have one-dimensional chain. I will now extrapolate that to 2 dimensions. And here I have 4 different arrangements that like the chains that I showed you before. So just assume that every set of 4 orbitals is actually an infinite 2-dimensional plane with a lot of atoms in this kind of square net arrangement. Again, we can have them all the same color, never change color, everybody's happy, low energy. See, same principle as before. If we can see that we can change color always in one direction, we can change color always when we go in the other direction, or we can change color regardless of which direction we're going in. And you can also see that these two should be energetically the same when we only change color in one direction, because the total color changing situations are the same. While the one where we change color in both directions will be highest energy, because electrons don't like that. And so we can again draw this little diagram, and we can say, okay, so when we have all the same color, then that is low energy, and I can go up to this situation where I'm changing one or the other direction, but then I can go even higher up to where the color changes in both directions. And so if you think in this picture on the left, I'm actually going from this situation to this situation, and then from this situation up, and then from that one diagonally back down. And so then we get this kind of a band. But since this is a 2-dimensional crystal, actually these wave vectors, these k's, or the directions in which we change color, are independent. And so we kind of want to represent them independently. And so we won't draw them on a single line, but rather on a plane where we have kx that changes in one direction, and ky that represents the change in the other direction. If we do that, then our band becomes this 2-dimensional surface in the 3-dimensional energy and 2-wave vector space. And this describes the behavior of our electrons. How? Why? Well, let me tell you. For one thing, in this description of a band, in this E versus K diagram, we can very easily read off the velocity of any electron in the band. We just pick any spot on this surface that will represent one quantum state of an electron. There's an electron there, excellent. And then we look at the slope of this surface. And the slope of the surface just gives us the velocity of the electron. And the direction is perpendicular to that slope. Okay, so just looking at this, looking where the steep bits of the band are, that's where fast electrons live. Here on the bottom and on the top, where the bands are relatively flat, these are not very fast. Okay. So if we could just know what the bands look like, we know a lot about the electrons. We know the direction in which they're going, we know how fast they're going. And just so we don't leave it at just one single band, I told you in the beginning that in atoms we have many atomic orbitals. And if we have a hydrogen atom, then we only have one electron, so that lives in only one orbital at a time. But the world is built up of many different atoms, and they will have different numbers of electrons, and so many different orbitals will be populated. And each of the atomic orbitals, when they come together in the solid state, will form bands of their own. And so we will get one band for this round-looking one. We will get a different one for this dumbbell-shaped orbital. And then the bands that they make, they can overlap, they can intersect, they can be completely separated, like I've drawn here. And you can see that they can have generally different shapes and different behavior. And so, in the same way that I told you in the atoms, these bands represent, instead of atomic orbitals, call them crystal orbitals. Okay? So these are the electronic states for the entire crystal. And the same way that we were filling up atomic and molecular orbitals from low energy states up to higher ones, because electrons don't like to play with their friends. It's going to be the same situation in these bands, in these crystal orbitals. So let me illustrate this on this example of the purple band that I keep moving around the slide. Okay, so when we just put the band there, we don't yet put any electrons in it, so it's an empty box, or rather, in the case of bands, an empty collection of boxes. And then we start putting electrons in. And as I told you, electrons like to first go into lowest energy states. So what's going to happen here is, as we start putting more and more electrons in, they will always try to settle on the bottom. And so you will always be able to make a cut at some constant energy where the last electrons sat down. And everything above that is empty, and everything below that is full of electrons. That's why there's a little energy arrow next to the diagram. And what I'll show you in the center is what is the shape that you get when you make that cut across constant energy where we ran out of electrons. Sorry. When we don't put any electrons in, obviously there's no shape, there's no electrons inside. The energy is somewhere below. If we put a few electrons in, we start populating this minimum in the center, and you can imagine that that is a roundish thing, so a cut across it will be some kind of a tiny circle. We put more electrons in, bigger circle. Right? We're going from a minimum, this is getting wider and wider. When we get to about halfway, then that expanding circle hits the sides, which, as I told you before, is kind of the maximum frequency at which the electrons can change colors. So we can't go any further. And then as you start filling more and more, you see that now we're starting to go up these peaks towards the corners, towards those states where I said the color changed in both directions. And that starts closing the circle again around that corner point. We fill it almost to the top, tiny circles around the corner. And when we fill it completely, we don't have any curve inside anymore because the entire band is filled. And so we can look at this sequence of shapes and different fillings that I told you about, and I can ask something about the properties and the behavior of the electrons in different situations. When there are no electrons in the band, if you try and think about the conductivity of such a material that has a band, it's empty, there's nothing to carry the current, then there's no current, it's an insulator. Okay, no surprise. if you have some electrons in the band is partially filled, you have this line of that kind of delineates the filled and empty states. These kinds of things are metals. There's electrons in the band. You put some voltage on, current flows. Excellent. Not that surprising again. But what happens when you fill it completely? Well, you might think, okay, it's full of electrons now, even more of them. Look how steep that is. The electrons whizzing around across the entire crystal. We know that if we have a band, that means that the electrons are hopping around. That's how we kind of constructed the band in the first place. And we know that they actually end up having very high velocities because of how steep these things are. But it turns out that if you fill the band completely, it's an insulator again. And this is another parallel with atoms and with molecules of a property that I didn't mention ahead. And that's that if you have atoms which have some orbital completely filled, or some collection of like orbitals completely filled, then they're fairly inert. They don't really hang out with anybody else. They're happy alone as they are. So it's very difficult to get them to interact with the outside world. Same with molecules. That's actually why molecules form. Atoms decide to share electrons so that everybody kind of fills up their orbitals, and so they don't need to hang out with anybody else anymore. That parallel kind of translates into bands. If you completely fill it, then it doesn't really care about external poking and perturbations. It's perfectly happy just sitting there and not doing anything, and you won't get any current if you put voltage on top. If you want a kind of a one level higher explanation of why, because you might still ask, okay, but you just told me that the electrons are running around. Now you're saying they don't care. Yeah, but if you fill the band completely, then you always have exactly the same amount of electrons going that way as going that way, going that way as going that way. So all of the velocities in the band just cancel out. Doesn't matter what you do to it, there is no way to get any kind of imbalance because all the states are full. And so you can't get any current. But it turns out that if you take empty band or completely filled band, and you put a little bit of impurities that either contribute a few electrons or take a few electrons away from the band, then you get yourself into this situation where you have teeny tiny pockets appearing again. And then we're talking about doped semiconductors. And you see this understanding of behavior of electrons in metals, in semiconductors. What does it mean when you have just a tiny amount of electrons? What does it mean when you have this tiny pocket at the top of the band? How do those interact? How do they behave? What can we do with that? That curiosity and kind of fundamental research into understanding of band structure of what we now consider somewhat simple materials, even though we're still discovering very exciting new things in them, is what drove the semiconductor industry, the electronics, and the information age in which we live today. I can also just tell you a few more things on these shapes while I have them, and you won't be too surprised if I tell you that when you look at these shapes, let's say from the top here, and these cuts, the exact surface area that's enclosed, or the states that are occupied, if you just look at the surface area here with respect to the surface area of this boundary, turns out that actually directly gives you the number of electrons in that band. which, I mean, to one degree, no surprise, right? You start filling it up, it's a tiny little thing, you put more electrons in, it becomes bigger, you put even more, it's half of the surface area when you're, as I said earlier, half filling. You put even more, the empty bit starts shrinking towards the corner until you're completely filled. So if we make a measurement, if in some way we could measure what these shapes are, how big they are, what the slope of these bands are, we would know velocities, we would know how many electrons there are in materials. We very quickly learn a lot about a certain material. Okay, let me recap a little bit this introduction into band structure and electronic behavior. So I said we take some atoms, we put them together in some orderly arrangement, which we call crystals, and that is what we know as solid-state materials. Then we can think about the atomic orbitals, which, when the atoms are close enough that the electrons can hop from one orbital to the other, when they have that overlap, they will create these bands. Okay? And we can think of these bands as the orbitals of the crystal, the electronic states of the crystal. We represent the bands in these energy versus K diagrams, and when we draw those, we can fill them up with however many electrons we have in the system, and then from the shape of these curves and from the shape from the shape of that constant energy cut, what I said when we ran out of electrons, we can learn a lot about the behavior of the material. Right? So I said we can learn about the filling just from seeing how big those shapes are. We can learn about the conductivity and the conducting behavior from the velocities of the electrons, from the shapes, positions of these curves. And we can learn a lot about these velocities of electrons by looking at the shapes and the slopes of these bands as we measure them. Yes, okay, Igor, you've been talking for 35 minutes now, but you promised to tell us how we look at them and how we actually see them. So I wanted to give you an introduction of what you should expect and what happens when we look at the behavior of electrons in the solid state. And now I'll show you a little bit about how we actually do that and what these bands look like in real materials and what other properties we can investigate with the experimental techniques. So, how do we see the bands? Pun intended, we get a flashlight and we shine light on them, literally. So this is a little cartoony depiction of how the experiment works, but I will try to explain step by step. The experiment is called Angle Result Photoemission Spectroscopy. Horrible name, I don't know who came up with it. It's too long, too cumbersome, but I will break it down. And as all best explanations, I will start bang from the middle. So let's see what this photoemission means. This refers to the photoelectric effect, which is something that actually Einstein won the Nobel Prize for explaining. And it turns out that if you shine a light on a material, you can kick out electrons from the surface. That's the photoelectric effect. That is photoemission. Now, if you are smart about collecting the electrons that fly out, you can measure their kinetic energy. Measuring the energy of something is, in the jargon, called spectroscopy. That's two words we ticked off. And the other thing that you can measure is the angle at which the electrons flew away from the surface, and that's the angle resolved part. And now I promised the keen amongst you 2 slides with equations, so this is the second one. It turns out that by knowing that kinetic energy and by knowing the angle at which the electrons fly out, we can use some of the basic principles in physics: conservation of energy and conservation of momentum. From the conservation of energy, we can take the kinetic energy of the electron that flew out, and we can calculate what the energy of that electron was in the crystal before we so rudely evicted it from its home. Also, when we know the kinetic energy and this angle at which the electron left the surface, that angle tells us something about the momentum that the electron had within the crystal, and it just so turns out that in quantum mechanics that momentum is tied to our K. And so we have these 2 equations. By measuring the emission angle and the kinetic energy of the electrons, we can find the energy of the electron before it left the crystal and the K of the electron before it left the crystal. And you know by now, because I keep going on about it, that if we know exactly the position of the electron in this energy K diagram, that is what the band is. If we collect enough of them from all different parts, we will get the full band and we will know how the electrons behave in the crystal. And the advertised data from the title slide, you have, again, this cube that I showed in a cartoon on previous slides, but here you have the binding energy of the electron, and you have this K in 2 directions for the material in question. And so you can recognize these lines as the electronic bands. These are the states that describe the behavior of electrons in a material. And also this top constant energy cut is simply when when nature ran out of electrons in making this material. And the shapes that you see on that top surface describe the behavior of the electrons that were the last ones in, the ones with the highest energy. And it turns out that those are the ones that are responsible for interaction with the outside world. And so by looking at the shapes at that last occupied energy, by looking at the shapes of the dispersions, we can learn a lot about the behavior of electrons in this particular material or in any other one. Right, so that's the general idea of how the experiment works in principle, but how do we do it in practice? Where do we do it? So the experiment itself is usually done in a big, complicated-looking submarine thing. Is the best description that I can come up with. Because we have these free-flying electrons when we kick them off of the material, so everything needs to be in ultra-high vacuum. And that means that we need these big submarine-like chambers so that we can keep a very high vacuum so that we can be very precise about measuring the properties of our electrons. Everything tacked on top, or most of the things tacked on top here, are to keep that vacuum. And then you might ask, what is this big donut thing? Donut-looking building. If anybody saw the 3-body problem Netflix show, they might have actually seen this as the Oxford University particle accelerator. Turns out it is a particle accelerator, just not the kind that they were talking about in the show, and it is in Oxfordshire. What this is for us and for our experiments is a flashlight. So this is our light source. We have, why I said it's a particle accelerator, we have electrons zooming around in this big circle, but when electrons zoom around in a big circle, they radiate light outwards, and we use that light to then do our experiments. So yeah, big expensive flashlight, but it's wonderful. Lovely doing work in there. And this is roughly what a day in the office looks like. Sometimes it's more hands-on, sometimes less. Sometimes you get puffs of smoke above your head. Hey, it pays the bills. How much time do I have? Not too much. Okay, I will speed up a little bit, and I will tell you about just a little bit about different flavors of this experiment that we can do. We can change different parameters of the experiment and learn different things about the electronic structure. For example, if we use linearly polarized light, we, for reasons that I won't go into, become sensitive to different atomic orbitals that originally built up certain bands. So here, if we use this vertically polarized light, we are sensitive to this band. If we use horizontally polarized light, we're sensitive to this band. See, there are two bands there. But depending on which light polarization we choose, we can focus on the one that we want. We can play more with light polarization. We can use circularly polarized light, in which case we are sensitive to the angular momentum of the electrons, something about how they spin around. In this experiment, circularly polarized light one way or circularly polarized light the other way picks out opposite angular momentum for these bands. We can also, for the electrons that we shoot out, we can ask them what direction their spin is oriented in. And so when we measure some kind of a band structure, we can also try and see if there is some spin polarization, and in certain situations, you will get bands that only consist of spin pointing up or only consist of spins pointing down. Or in more complicated situations like this one, where you again might recognize stuff from the title slide, we have these two ellipses, and the spins of the electrons around the ellipse rotate in this really funky way. Again, won't go into the details of why this is exciting. I won't yet say that it's useful. But if we're talking about useful, we can also make little devices out of all the exciting new materials that we investigate. And we can look at the behavior of electrons while the device is in operation. And with that idea of building new electronics, building new devices, I will just give you a little bit of a flavor of what I said early on, that in this enormous agglomeration of a large number of atoms and a large number of electrons, the phenomena that comes out is extremely rich, and we are still figuring out what new things are possible. So I'll just flash a few pictures of weird phenomena. One is superconductivity, which people may or may not have heard of. The idea is that materials conduct electricity with no resistance. But not only that, these materials are what are known as perfect diamagnets, which means you can float the magnet on top of it. You want to see what that looks like? Come to our open day on Saturday. Condensed Matter Group does a demo. Advertisement, right? In other situations, you might get the electrons grouping periodically into little groups like this. That will dramatically affect the electronic structure. And that will have a knock-on effect on the crystal structure. So you get this connection between the arrangement of the atoms and the energetics of the electrons running around. And finally, a category of materials known as topological materials or topological electronic structure, for which actually the work that originally predicted topology in physics, let's say to a degree, don't quote me on that, but was awarded to two professors who did that work in Birmingham. And it's been a revolution in condensed matter physics with all kinds of different topological materials coming about, and with some applications that we can do because some of them host very robust protected spin polarized currents along their edges. So all kinds of new different properties that we can investigate, but not only investigate but also engineer. So the idea is that looking forward, we understand more and more of these phenomena, we understand where the phenomena comes from, and we can try messing around with the materials to engineer the electronic properties that we want. One step towards that is taking ultra-thin, atomically thin layers of different materials, stacking them on top of each other. First step is thinning things down, seeing how things behave when they're thin instead of a big chunk of crystal. Second step is start messing around with stacking of different materials of different 2D sheets. And we get wonderful different properties from that. You can do that by literally scotch tape, sticking a scotch tape on a crystal and pulling it off, some of it's left on, sticking that onto a different thing. Or you can grow it from bottom up, if you will, by kind of doing crystal growth in 2 dimensions. People also do in this scotch tape method. They pull it off, they rotate it by a little bit and stick it back down. Turns out, fascinating new phenomena. Again, I won't get into the details of that, but we can also create new electronic structures by poking it with different light pulses. We can also, something that we do in our group here in Birmingham, change the electronic structures of things by squeezing them in different ways. And with that kind of taster and flavor for what's possible, I will thank you for your attention and leave you again with an atomic orbit. Thank you.